Hello there, everybody, and welcome. It's Professor Thayer here with you to talk to you another lecture on physical chemistry. Tonight we are going to talk about liquid solutions. So let's do this as the usual way. I will now share my screen with you, and need to go here and put this down. So getting the Zoom meeting up and running. And now let's put this in full screen mode. All right, and we are good to go. I wish this Zoom thing would get out of the way. Okay, can we move it? All right. It used to like automatically roll up so I could click on it. And not display it. I guess you probably can't see it, but it blocks my screen. No, I don't want to see the meeting. All right, minus be small. Is this thing? No, all right. Anyways, I guess this is gonna be in the way for me, this meeting too. All right, anyways, start recording. We are talking about liquid solutions. Now, in biology, liquid solutions are obviously highly important because things are mostly in the liquid phase. So this, are you sharing the screen? Okay, share entire screen. Done. Okay, now the screen is like showing me a mini screen for me. I want this to be small, out of the way, go away. All right, anyways, just deal with it. All right, so we're going to be applying the thermodynamic principles to solutions. And solutions are really important for biology because most everything exists in water. Our human bodies are something like 75% water, somewhere around that, 65–75% water. So water is really important because molecules are almost always in solution. So we want to take a look at what happens when you have one solution mixed into another solution. We work with partial molar quantities, which leads to the Gibbs-Duhem equation, and also Raoult's law. So these are for simple ideal solutions, of course. All of these things are idealized, which is not always the case in real life, but most of what we know stems from idealized solutions and then is applied as a correction to that. So starting with the idealized ones is a great place, and when solutions aren't ideal, non-ideality can be described as approximations to that. So let's get into it. What is the partial molar quantities are important for thermodynamic properties of solutions. Partial molar quantities. Important. Thermal properties of solutions. All right, so our discussion of solutions will consider systems with two components. We'll have N1 moles of component 1. And guess what? N2 moles of component 2. And what we want to do is we want to write the Gibbs free energy. All right. So this means that the Gibbs free energy is gonna be G of temperature, pressure, and the number of moles 1 and the number of moles 2. Okay, these are number of moles of each of 2 components. All right. So let's go ahead and write. So dg equals dg over dt. Now we're going to put the things that are P and 1 and 2 dt. So what does this say? This says that it is looking at the change in the Gibbs free energy with respect to temperature. That's why we have dt over here. And the things that are being held constant are pressure and the number of moles. So when you have some stuff in your solution, you can't change the amount of stuff in the solution. All right, plus dg dp. All right, so now we're going to consider the other part of the equation, dg or dp of T and 1 and 2. All right, dp. Again, now we're going to say, all right, partial with respect to pressure. Okay, we're going to hold the temperature constant at this term, and the number of moles stays the same. And now we could have the part that has the contribution for the changes in mole 1. So plus dg dn1, and we'll hold the other things constant, pressure, temperature, and n2 dn1 plus dg dn2 with pressure, temperature, and n1 being held constant, dn2. All right, not surprising. And it takes into account each of the various components that we have. All right. Consider that the composition of the solution is fixed. So this means you're not changing what's in the beaker during the prescribed time under consideration. D n1 equals D n2 equals 0. That means no changes in the number of moles. That's what that says. Then we can make the following equivalencies. So dg dt of dn1 n2 and n2 That's a comma, not a one. And that's got a comma and a one. Is that clear? It's probably not that clear. It's right here. Okay. N one comma N2. Right, that's better. Equals negative S of P T N1 and N2. And dGdP temperature N1 and N2 equals negative V T N1 and N2. So the derivative of G with respect to the number of moles M is defined to be chemical potential mu. Now we're back to the chemical potential. All right. And looks like the first view. Several use equivalencies and definitions above. Look at this. Okay, so what we're gonna do is we're gonna sum in the pieces that we just wrote about. Hold on. So let's write it out and then let's find where the pieces came from. All right. So dg equals negative s dt plus v dp plus mu1 d mu1 plus mu2 mu2. All right, now some of these pieces came from some of the things we just wrote up here. I do believe this. Yeah, so these are coming from these parts that we just put up here. That's why we were interested in getting these. Now, see, we have this equivalency for the change of Gibbs with respect to temperature. Is going to be the entropy with this one with dt, right? So this will be this one dt, and this one, which is for the Gibbs with respect to pressure, is v dp, right? And the reason why we have those is because we have the dt and the dp from these parts up here, okay? So that's why we have these equivalencies that we substituted in. So we could even color code pieces so we could keep track of them. All right. So shall we do it in rainbow order? Let's have a red one. Okay, it's this one dt, which has to do with this information here. And this information here is corresponding to that, which corresponds to this term here. Now we also have the pressure one. The color says pressure to you. I don't know, gray actually. How about gray? All right. So this is our pressure term right here. Oh, it's pastel colors. Kind of. All right, and this is our information about pressure. Okay, right there. And that came down and went to this place here. Okay, and then we have our moles to the N1s and the N2s. Which of these? We didn't really do much with those. So I think we can leave that like that. But the number of moles isn't changing, so let's see if it happens. Okay. Now we have this equation. So what can we do? Okay. The partial molar quantities are denoted. Okay. Like so. Partial molar quantities. Okay, this is the generic. Equals of TP and 1 and 2. Okay, and now we have the partial molar quantity. Y bar sub J, okay, equals Y bar sub J of T, T, N1 and N2, like so, equals partial of Y, the partial of NJ with T, P, and D, and I is not equal to NJ, in other words, not to itself. All right. I need to take some notes there. This is all except NJ. Right. So in other words, when you have, oh wait, I forgot to put the not equals. I not equal to NJ. Yeah, that's better. So you can't like interact with yourself, which is why we have NI not equal to NJ. But it's a pairwise interaction indication here. Okay, totally one partial molar entropy. How would we write that? So this would be SJ. By the way, the bars are for the molar quantities, right? Right, so this is like entropy per mole of gas. Right, that's what that means. So SJ equals SJ bar PN N1 into equals DS DNJ of TP and I is not equal to. Did I put, yeah, this is why this doesn't really make sense. Yeah, it's just I not equal to J. Sorry, that this make more sense, right? The point is the particle can't interact with itself. That's all that means. I just copied it wrong. Sorry. Measure how Y or S changes and NG changes. And all right. So in other words, the Y means some extensive thermodynamic property. That's right. Or some extensive thermodynamic. And extensive means it's going to be the molar value of it, which is why we have the Y bars here. So here we just wrote this generic thing and then we wrote it for some Yj, right? Some particular instance. And but that still is not particular, that's not a specific thermodynamic property. So we picked a thermodynamic property, we picked entropy, right? So in other words, Y means some thermodynamic property, and entropy is the one that we picked. So here we wrote it out for entropy. So in other words, we just wrote it in the generic form, and now we wrote it for entropy. Suppose we want to write the chemical potential of a two-component system. This is described by Bloom equation. All right. So it goes like this: x1 du1 plus x2 0. Constant temperature and pressure. By the way, x1 and x2 are million fractions. And chemical potential of one component the chemical potential that can be produced. Which is calculated. We can add to equilibrium. Chemical potential each component has the same value in each phase in which the component appears. So let's see what this means. We could then write Vg total equals Vg of the solution plus Vg in the vapor state. Maybe we'll just write VAP for short. So the total, in other words, is the sum of the parts. So we could rewrite in potential in terms of the chemical potential. This is the kind of familiar from the previous chapter. Yeah. Right in terms of the chemical potential. Okay, solution. Okay, solution. J vaporization. And vaporization. Oh, looks like a Venn diagram right in this. Let's see. If the system is a change in chemical potential, of component J in vaporization equals the change in the chemical potential in the solution. So we kind of saw this already when we saw, well, when some particles would evaporate, then there would be a chemical potential for the ones that evaporated to go into solution. So in other words, the system is exchanging from one phase to another. So we can write that J of vaporization equals mu J of the solution. If the system is ideal, we can write the pressure of the component J. So we can write this. Pressure J equals xj p star J. This is Raoult's law. What's the star? Star is like this one right up here. I really need to write it better. Let me make it better. There you go. Pure liquid component. So yeah, let's just be clear what exactly that means, because that was also not totally obvious. For example, if it were just component J. So, in other words, we're assuming additivity here. So of course things might interact. We're assuming they don't. And the star is when it's the part that's, if it were just by itself. PJ equals pressure J in the mixed solution. XJ, mole fraction of component J. Once in a while, it kind of does some really weird things like that. A giant fine. Component J. P star J, then is the pressure of component J if we were not in a mixture. Some of these things are a little bit hypothetical, as you might imagine. All right, great. What makes an ideal solution? All right, let's take a look. Let me draw a beaker over here. It's kind of like my pistons, but it's not a piston. So now it's a beaker. There you go. And we're going to have some, where this one, we need the background. We're going to have some things in the beaker, some solids. Looks like marbles, but it's going to be particles. Okay, but they're mixed. And so some of them are different than the others. And there's a couple that are filled in with the ones that use a little. All right, so you get the idea. We have a solution here in some. Okay. What about this? So say two types of molecules. One that's filled in and one that's not. Types of molecules are distributed randomly throughout the solution. All right, so in other words, what we're imagining here is there's no phase separation or no precipitation or other funky stuff going on. No phase separation, no precipitates, no other weird things happening. Just two liquids, actually liquid form, and they're miscible, they're mixed together. Okay. We're also going to assume molecules are roughly the same size and shape. intermolecular forces in the pure liquid are similar such that the molecules interact with each other similarly to how they interact with their own kind. So you see, we're putting an awful lot of qualifiers on this. Intermolecular forces in the pure liquid are similar such that the molecules interact similarly with each other as they do with their own kind. In other words, this is not hydrophobic, hydrophilic stuff. All right. These same reasons are the reasons for non-ideality. Yeah. Are the parts, aspects giving rise to non-ideality, i.e. when they're not met, i.e. when they are not met, non-ideality happens. But let's assume that we're working with an ideal situation. All right, time for a graph. And let's take a look at what it means. So here we're going to have the vapor pressure versus fraction of alcohol from 0 to 1. We're going to be looking at alcohols in water. Okay, so the idea is we're going to look at a series of different alcohols in water versus the ideal situation. So the vapor pressure would be perfectly linear. So we'll go up to 1, okay, perfectly linear. This is the ideal situation. So if an alcohol were ideal, or you could think of it as the ideal solution. Yeah, which of course doesn't exist, but it's always nice to dream, right? Okay, so now we're going to take a look at some different curves. So we got methanol, ethanol, and 1 propanol. Let's draw some curves here like this. Let me draw the most extreme one. It's like this. They all sort of end up like, all right, well, this is the end point, which comes down to 1. This is, by the way, I use fraction. Okay, so in other words, you had no alcohol in there up to having it full of alcohol, and we're drawing the curves for a specific alcohol. So if everything were ideal, it would just be a straight line, but it's not a straight line for real alcohols. So here we have several alcohols. I kind of didn't leave enough space for labeling. Let's label it like this: 1, 2, and 3. All right. Let's curve 1. This is methanol. Okay, how is methanol? CH3OH, methaprop, remember? Okay, methanol. So that's this one. 2 is ethanol. Ethanol. CH3, CH2, OH, right? OH group on there. And so you can see what's happening here. We're growing the hydrocarbon chain on the alcohol. Will be 1 propanol, CH3, CH2, CH2. Okay. So as the chain gets longer, what's happening? It's getting less and less ideal because it's less and less like water. The OH part is not terrible next to water, right? So you have H2O or HOH. You can consider it's like HOH, and then you have the thing that's attached is going to be CH3OH, and then it's going to go to, you get the idea, CH3CH2OH, and you got CH3CH2CH2OH, right? So this part is not horrible, but it gets worse and worse. So this is why the non-ideality also follows exactly that trend. So as it gets longer and longer, this is going to be more and more of a hydrocarbon, which does not really like to be near water. The OH part is fine with it, but the CH3 part is not too happy to be in there because it's hydrophobic. And as you increase the fraction of alcohol, this is going to behave like this. So let's take a few notes. With increasing size, alcohols make solutions which are less ideal as they're increasingly dissimilar to water. So we might think about this when we're thinking about molecules, right? So solutions in the body are probably not really very much like ideal solutions at all because they have many components, and those components are definitely way less like water than alcohols. So they're much larger. An ideal solution, 2 components. Pressure is given by this equation. Pressure total equals the sum of the 2 pressures, P1 plus P2. And then we can write this out just like we did before. The fraction 1 P1 star plus 2 2 star. Yes, just 1 plus. And this is weird stuff. Maybe there's some X's on here that are broken or something. Okay, we have chi1 plus chi2 equals 1, i.e. fraction sum to 1. So now we can write the total equals 1 minus chi2 p1 star plus chi2 p star 2, which reduce the number of variables. Because we could write our own change in just one thing. All right, so let's do an example. One propanol and 2 propanol form an essentially ideal solution. Let's go ahead and assign them. Then we'll assign this to subscript number 1, and we'll assign this to subscript number 2. Or a problem, right? If we could assign them either way, right? But let's just do it like that so we can keep track. So P1 star equals 20.9 torrs at 25 degrees Celsius, and P2 star equals 45.2 torrs at 25 degrees Celsius. And now we have a question like this: calculate total vapor pressure at 2 equals 0.75. All right, so how would we solve this? Let's say we have x total equals chi1 or x1 plus x2. That's the equals. That's the mole fraction definition. That's given. Okay. Now we're going to solve for x1. All right, so xt is on the left, but we're going to rearrange. All right, so how are we going to do this? So in other words, xt, it could be substituted in for 1, right? So the whole thing is equal to just 1, right? So I could use that. Okay, so I'm just going to rearrange, and I'm going to have x1 equals 1.00 minus x2, right? Because that's the number for xt. And now I can substitute in my information. So I said x2 equals 0.75. So we substitute that in. So x1 equals 1.00 minus 0.75. So it's x1 equals 0.25. Right, algebra is easy. Let's make sure you calculate the correct thing. All right, but we're not done yet because we need to calculate the total vapor pressure. So how do we do this? The total equals chi1 u1 star plus u e2 star. All right, this is given. Equation from above. Now we're going to substitute in the total equals 0.25. That's what we just solved for. 20.9 towards the pressure plus 0.75 towards, this is all at 25 degrees Celsius, by the way. And then you just solve is equal to 39.1. You just multiply it out and add up. What would happen if the gas burned ideal? Let's do that. Let's consider. Formula holds when the gas behaves ideally, right? That is, the gas contributes its fractional component times its usual pressure when the gas is ideal. When the gas isn't ideal, there could be interactions between two gas types, and that's what would make it be something else. And so then we'll need to figure out how we could deal with that. So let's capture that thought. That is, the gas contributes its fractional components times its usual pressure. Usual pressure, meaning when it's pressure by itself, when the gas is ideal. When the gas isn't ideal, there could be interactions. Between the two types of gas. Making the contribution of something else. And this brings us then to the activity. So if the gas had some interactions between itself and the other gas, then that means that it may not be available 100%. The amount of activity that it has wouldn't be 100% of what its activity is when it's ideal. You could think of it as like it's somehow being modulated or dampened or needs a correction factor. That's probably a good way to think about it. And that brings us to the activity. Okay, so the activity is a way to sort of like make a correction for the interactions. And so if we were able to somehow have a correction factor, we could continue to use the ideal gas equation with the correction factor. And that's exactly where it's going. So activity is our next topic. Activity. A sub J is the activity, which is a measure of pressure difference. In other words, aka non-ideality due to interaction. Okay, that's what we're talking about. AJ. Yeah, weird. Why is the pen do that? I don't know. AJ equals PJ over P star J. This is the pressure J when it's by itself. And this is the partial pressure of J in solution. The activity coefficient activity per mole fraction. That's the activity per mole fraction. It's supposed to be the activity. Oh, yeah, that's because it doesn't have. I like it's I think a gamma. Like that. Is that better? That's just that's lowercase, right? That's a gamma. Gamma sub J. So the activity is going to be measured with respect to a standard state. Therefore, the activity coefficient is also with respect to a standard state. Gamma is also with respect to a standard state. So now you can put it all together in terms of the Gibbs free energy, which will tell us about whether things are going to mix or not. So the Gibbs free energy. For mixing can be expressed by ideal terms and correction terms for the non-ideality. All right. right, so let's write the equation. This is called the Gibbs molar energy of mixing. Gibbs molar energy of mixing. So to G bar, so this is molar, right? Mixing over RT equals X I1 ln I1 plus I2 ln I2 plus X1 ln gamma. Oops, gamma. That doesn't look like a gamma. Let's fix that. Gamma. Chi1 ln gamma 1 plus Chi2 ln gamma 2. So in other words, what we have here then is 2 x. Oops, I thought we just changed that. Change this. That. This. All right. So this part over here is for the ideal solution. And the part over here has all these gammas in it. These are the correction terms. Right? So it uses the activity coefficient for real solutions. All right, so then taking a look at this, we have now described a new equation. All right, so let's go through and summarize what we have seen here for the day. We also need to pick out our important equations for today. So here's our highlighter. So we have our Gibbs molar energy of mixing right here. Let's color that in. Here we go. And we have the definition, major equations, and we have seen about the this is another one of our key findings for the day. Is total pressure and the fractional pressure, right? So that. And let's just go through here. Talk about ideal solutions. Yep. Raoult's law. We have also discussed today. Let's capture this one. And all right, we've done our fraction of Gibbs free energies. Also is the major equation we got today. We broke out this. Another important one. Chemical potential equation. We should have quite a few equations today. Okay, chemical equation, chemical potential, partial molar quantities. Yeah, and let's see, partial molar quantities. This is our generic, and then we broke this out into the individual ones. And we also talked about the Gibbs free energy to get our total. So we have this equation down here, which we have already done a bit of coloring, so I don't want to ruin that. Okay, there. So let's now summarize what we have talked about today. So today has been a discussion about partial molar quantities in thermodynamics and properties of solutions. So solutions are obviously pretty important to PChem because much of what the human body operates on assumes that things are going to be in solution, right? So we need to understand about things dissolving and other things. So if we want to write the Gibbs free energy for that, we can do so, and we can make use of, again, some of these very Maxwellian-esque kinds of um, relationships to write that out. And so we are able to write out Gibbs free energy equivalency right down here. All right, let's get my what is this? Participants one, host. You can now send nonverbal feedback. We don't need to see that right now. Okay, great. Okay, so this is how we were able to derive our equivalencies. Here's my wicked cool pointer, which draws things and then lets them go. So we did the derivation right here. And then we were able to arrive at this equation here for the Gibbs free energy relationships about solutions being dissolved that have multiple components in them. So then the next thing we wanted to do is to look at the partial molar quantities. And we took a look at this right here, for example, right? This was the generic solution, and we discussed how you can come up with the partial molar quantities. This is when you have a solution that may have pieces in it, right? And one can solve this when you have different parts in your solution. And we also have the partial molar entropy as a specific example, because this was just a generic one. But one could in fact write this for other things as well. And don't forget, also we have this bar, right? So these things are all per mole of gas. That's what that means. The next thing we looked at was the chemical potential of a two-component system. So we've already seen the chemical potential, right? So this is revisiting that chemical potential of a two-component system, but we haven't seen that yet. So we wanted to write the Gibbs-Duhem equation, which then tells us about that chemical potential. Oh, lights just came on. Chemical potential for a two-component system where we're now working with the fractions, right? So we have x1 plus x2 equals x total, right? Which we actually made note of further down. So knowing the mole fractions and the chemical potential, we are able to write out the total Gibbs free energy, which we did right here. And we are able to rewrite in terms of the chemical potentials. So this is the Gibbs free energy. It's actually probably worth noting. This is the Gibbs free energy. Gibbs free energy in terms of the chemical potential. A very useful equation. This one right here is for that equation right there. So if the system is closed, which we're usually dealing with, we also were able to realize that the change in vaporization was going to the equivalent. So this actually was not new. We saw that prior. And so we basically arrived at the same place where we've been at before. Okay, so if the system is ideal, we can write some important information. So for example, we have Raoult's law. So the Pj equals xj times Pj star. So we're dealing with starting to deal with some of the corrections. So we're saying about the fraction, right? The fraction of J and whether and about its contributions is the pressure component of J if it were not in the mixture. So this is how much it is, and this is if it were not in the mixture, and this tells us how much it's going to be for our actual mixture. And we started talking about ideal solutions. So we drew this now the picture of an idealized solution, and we have a mixture of two things distributed. And we have a whole list of 3 things that would have to be true for this to be an ideal solution. 2 types are distributed randomly, so there can't be any phase precipitation, phase separation, precipitation. You can't have difference in size and shape, and you can't have any interactions with how they interact with each other as compared to themselves. And so we took a series of alcohols, which really are not maybe too hugely different from each other than the size component. So this is a pretty reasonable comparison set. And we looked at the ideal versus the non-ideal ones, and we were able to trace out the trends here. So as we have the increasing size, then we have increasing amount of non-ideality in the behavior. As we can see, the ideal is this nice straight line, and these are not following a straight line. So then we looked at an ideal solution of 2 components. We could calculate the pressure, which we got here. So again, it's going to be quite similar to what we had seen before, right? So we've already been talking about from Raoult's law, this idea of the partial pressures. And so we could use that then to get that for an ideal solution. And the partial pressure is actually helpful because we could, in fact, actually start solving some actual examples. So here we are going to illustrate the example of calculating an unknown pressure. But what if it weren't ideal? Then we would have some problems. So what would those problems stem from? It would be exactly all the things we just said about what we had assumed for ideality. So the formula wouldn't hold for the reasons that we've already said, but we could then start working on activity. And so the whole idea of the activity is to try to correct for that. So we have this AJ, the activity, which is a measure of the pressure differences. So you might be able to come up with some idea about how there are some differences between the ideality and the non-ideality and have a correction factor for it. And that's what we're trying to do here. So we have the activities, the gamma. Actually, this is also kind of important. So I think we probably would warrant to go ahead and highlight this formula about the activity of our system, which is denoted by gamma, has AJ, right? The activity, which is measured pressure difference, the non-ideality due to the interaction over the fraction amount, which is xj. And so we took a look at this. And so we can see then that once we have this activity, we can use it as a correction factor. And we can plug that right into here. We can put it into the Gibbs free energy. So the Gibbs free energy over RT would be the ideal part of the solution. And we would also include the correction terms, which then would hopefully give us the actual observables from in the lab to allow us to describe what's actually happening. Alrighty then. That's what we have to say about solutions. Let's stop sharing and let me just come back. All right, well, I hope that you found that to be informative and helpful about these solutions. Talked about how we have multiple solutions mixed together, non-ideality, and ways to handle that very helpful when you're working with biomolecules, because a lot of times our systems are not ideal and we need to have ways to deal with that and also to calculate the Gibbs free energy for these things. All right, well, hope you enjoyed it. Thank you so much, and we will see you next time for more PChem.